Welcome to this special episode of Frequency Matters, the RF Microwave Update Series. I'm Pat Hindle, and I'm talking today with Ben Anino, Product Line Director at Analog Devices. Welcome back, Ben.
Thanks, Pat. Happy to be here.
So an exciting area these days is the space market, so I thought it'd be great to cover some of your insights into this sector. What factors are driving the space market now?
Yeah, so what we're seeing is a lot of LEO launches. So LEO is low Earth orbit, and that's really driven by these SpaceX and then Amazon LEO constellations that are going up that are going to support this whole SATCOM infrastructure. And there are going to be other players that emerge as well, but I think those are probably the two most established at the moment. SpaceX with a bit of a head start, but Amazon will be launching in the coming years. So that's driving is this commercial space style of product, which the life of these LEO satellites is only 5 years. So what that allows the LEO guys to do is buy commercial style parts that are much lower in cost. And so the replacement cadence of the satellites is a lot more frequent. And so they can have much lower price targets on the overall satellite. And we're also seeing a separate market for mid-Earth orbit and geosynchronous orbit, where the traditional satellite that's very expensive, it has a orbit that's further from Earth, so it's exposed to higher radiation effects. And we see a steady growth in this market as well. It's not as explosive as the LEO growth, but it's still a steady growth. And these geostationary satellites also have their place. So they're also used for communications links. They're also used for Earth observation and for a lot of military applications. So when it comes to national security, GEO is a really important orbit.
And so with all these LEO constellations going up, will space comms eventually replace terrestrial comms?
That's a great question. So the answer is no. Just the sheer amount of data throughput that a typical terrestrial base station has to handle is orders of magnitude beyond what space can accommodate. So we think that if you really look forward out to 10 years from now, even in the best case scenario, space traffic is probably only about 5% of the overall traffic. So maybe it'll handle a lot more than today, but it'll never fully replace the terrestrial networks. The satellite throughputs just can't handle what the terrestrial networks can handle. What the space networks are really aimed at doing is serving geo locations that don't have access to the terrestrial networks. So think about in large farming areas where there isn't much service, they could get satellite links to operate their machinery, things like that.
And so can you talk a little bit about phased arrays and the trends specific to SATCOM?
Right. So these satellites are equipped with phased array panels, and those panels are responsible for setting up beams to connect to user terminals on the ground. And these links are regulated. So there's bands that are dedicated to SATCOM links and NTN links. And so usually jammers aren't a huge concern. So linearity is usually pretty low. And most of the signal chain is designed for low noise. These are noise limited links. So satellites really need very low noise and very low DC power. This is a bit different from, say, a radar application where you might be jammed. And so you need a good blend of linearity, noise, and high dynamic range. The SATCOM links are usually favoring low noise.
And so can you tell me, what IC functions were popular in the past and how that's changing today into the future? I think, how are things being re-architectured because of this type of market?
Yeah. So when we look back to the 80s and 90s, like we sell a lot of linear components, like simple function op amps, voltage references, kind of single function chips at high rel. Going forward, we're expecting to sell a lot of your typical radio chain type components, RF components that complete that signal chain, whether it's for SATCOM, for non-terrestrial networks, or for military links. It's that typical RF to data converter to processor signal chain when we look into the future. So the op amps and the voltage references and the low frequency stuff is still going to be used, but we're definitely seeing a lot of growth in the RF signal chain, the RF digital sampling, and the power. Power is another really important aspect of space architectures going forward. High efficiency, low noise power delivery, linear regulators and whatnot.
Yeah, power is always hard to come by on a satellite. It's only limited. So how about for the same type of component, let's say, for example, an RF analog to digital converter, what performance metrics might be different for space applications versus a similar function that's used for terrestrial applications?
Right. Good question. So, like I said earlier, satellite applications have very strict power consumption targets. So usually the data converters that are used in space might have a lower number of bits, and they might be favoring lower DC power consumption. And so it's just basically just enough dynamic range, just enough sensitivity in order to close the link and have enough G over T, but also meeting a very strict power consumption target. Whereas terrestrial applications might require much higher dynamic range and might be willing to spend a lot more DC power to achieve that.
And you're definitely seeing some higher frequency applications. What are the 60 gigahertz and higher space transmit receiver links used for?
Yeah, so now that you have these meshes of satellites, satellite to satellite communication is very important. So these links at 60 gigahertz, that's a band that doesn't propagate well in the Earth atmosphere. It's a high absorption band. So it's a very nice band for space because you can use that for satellite to satellite, and you don't have to worry about any interference from the Earth or worry about those signals causing interference. So we're looking at a lot of applications where very high bandwidth links can be established satellite to satellite at the 60 gig and higher.
And so maybe you can wrap up with, what are some of the new ICs do you see coming this way that might be game changers in space applications?
Yeah. So what we see is because of this power limit and the constant need for better performance at lower power in space, we're seeing RF beamforming stick around. Some satellites are going towards every element digital. And so that's really requiring these low power, high performance data converters that are integrated with a lot of DSP to do the beamforming. So that's one strong trend. But on the RF beamforming side, a lot of constellations and a lot of links are sticking with the RF beamforming approach because it's the best of both worlds. You can use your RF beamforming to sum up to a node that's then sampled, and this helps save power. So I think rad hard high efficiency data converters and rad hard RF beamformers are going to be very important components going into the future, as well as rad hard power solutions, right? All sorts of high efficiency power solutions for space.
Well, thanks, Ben, for talking with me today about the space market and some of the important trends in semiconductors in this sector. Very interesting. To our audience, you can find more videos at videos.microwavejournal.com. Thanks for watching.